So Apache Cassandra, I'm going to start off with a bit of an intro just into NoSQL and distributed databases, very quick. And then we're going to go into a bit of a deep dive into Cassandra use cases, who's using Cassandra now, what they're using it for. And hopefully by the end of it, you'll understand a bit about the internals of Cassandra. You'll understand kind of who's using it and what for, and how to interact with it. And the drivers for Cassandra are all very similar depending on language. So we're going to have a look at the Java one. But all the other ones are really quite similar. So it should give you a good idea of how we as developers interact with Cassandra. Okay? So who am I? So I do work for DataStax. Has anyone heard of DataStax? Yeah. They basically build an enterprise version of Cassandra. They take it, they test it, they put their name on it, they embed a couple of other open source projects and then sell that. But I don't work with their products, really. I work with the open source version. So I think you can go to the Apache website and download and use for free and contribute to. And that's the only thing I'm going to talk about today. I've only just started doing this job. I was always building applications with Cassandra. So I used to work for Sky, and most of Sky's new applications, especially around internet television, are all built with Cassandra. I've also spent time in finance and building enterprise software with IBM. So I'm sorry about that. Okay, so what are we going to talk about? So distributed database, what type of databases have people used so far, just so I can kind of have good analogies. So relational databases, like Oracle, MySQL, those type of things. Who's ventured into the NoSQL world? So graph databases, document, Mongo, Couchbase, those type of things. Who's actually used Cassandra? I've got only one person to I'm good. Okay, so Cassandra is very much a distributed database. You don't pick Cassandra and then run it on a single node because it stops you from doing many of the things that we're used to doing in relational databases. And it does that for a reason, because it's expected to be deployed on many, many computers. So it stops you from doing silly things. But if you take it and deploy it on one node, you're just going to get annoyed because you're like, why can't I join? That's the first spoiler. You can't join in Cassandra. So we're going to talk about how Cassandra replicates data. Because one of the advantages of actually working with distributed databases, or depending on which one, is that you can handle computer failure. Okay, you can handle rack failure. You can handle entire data centers going down if you've deployed and replicated your data across multiple data centers. But you don't get all that for free. And we kind of, as developers, have to relearn how to model data. We're not going to be going into third normal form of Cassandra because we can't join. So that's kind of like the payoff. That's what we have to learn to take advantage of this. And then, as I said, we'll have a quick look at Java driver, and then I'll take some questions. Okay? So distributed databases. Why on earth would we distribute a database? It sounds a terrible idea. Okay? It's going to make things more complicated. It's going to add new failure mode. It's going to add latency. It's just a terrible, terrible idea. And there are a lot of them. So it can't be a terrible idea. And I've even included relational here, because most relational databases we can run in a clustered mechanism, right? Be it master slave, synchronous replication, asynchronous replication. So I'm going to include those. And then we've got lots of graph databases. Now, people generally use graph databases if their programming problem, the domain fits it, okay? Whereas key value stores, things like Dynamo DB that Amazon create, normally you're willing to sacrifice query functionality because you want some type of scalability or performance. And then document stores, which are, think of those as, I always like to think of them as JSON stores, right? They're like a key value store, but the database actually knows about what the format of the data is, so it can offer querying functionality, etc. And if you don't use any of that querying functionality, it just looks like a key value store. But the ones we're going to talk about today, and the ones that are kind of gaining popularity, are what we call wide row or columnar databases, okay? And these we can think of as developers as a map of maps. That's the simplest way you can kind of get your head around, columnar data stores. Say you've got a person, object. It's not, person name and then a blob. It's actually like person name, age, 20, person name, first name, Chris, that type of thing. That's it really. So we're just going to talk about a bit of motivation. So who here builds applications like this? So assuming you've got some clients, and you've probably got a database, which is going to be a big silver blob. And then you've got an application, which is a big blue blob. And you've only got one of each. Does anyone here build applications like this? Because a lot of companies do. And companies that I've worked at do. And during the release process, etc., we had downtime. Why do we have downtime? Because we have one blob. As soon as you turn the blob off, even if it's for a short time, you've got downtime. And if you've ever had like downtime during your release on a Friday night where they bring you in at 1 a.m. because that's when the least customers are on, you know fine well you probably have a single point of failure because they can't like do rolling releases. So we normally do things like this. This could be because we want to increase the amount of people that use our application, be it some type of web application. But another reason for deploying our applications like this is so that we can turn this one off and have no downtime. It adds complexity. We need to put load balancers in front of it. We need to design our application so they're not sticky. So when actually the next request for a user gets routed to this one, then they're not suddenly logged out. So if you're watching a movie on Sky Go and we decide to turn off half of our servers, then half the people aren't logged out with 5 minutes to go. That does happen. But the kind of like elephant in the room here, sorry, no, not yet. The thing about this is all of this kind of things here, I'm assuming are in a single data center, you know? And I don't think how many companies ago it was. It was about 3 companies ago. I'm not going to name a name, but you can work it out because they're in order. When we were just deployed to a single data center, we did have another data center, okay? If things went really, really badly, there was a disaster recovery plan, yeah? And it normally involved getting the entire tech company online until the disaster stopped, okay? Which was normally 8 hours or 16 hours, etc. And the reason you can't really have one data center, this has never happened to me. Has anyone had a tornado hit the data center? It has happened, but not to me. This one has happened to me. So when I was working at an American investment bank and the hurricanes hit New York, our data center was underwater for 1 week. That data center was not operational again for about 6 weeks. So if we'd been in a single data center, we'd have had 6 weeks of no trading of securities. I wouldn't have been too happy. We weren't active. Does anyone know what I mean by active? So if you've got 2 data centers, you've got 2 ways of using them. You either use them both all the time, that's active. Or you kind of have one which is either your backup or your hot standby, and there's some process which fails you over. That always involves downtime and it always goes wrong, and companies always get scared to practice it, okay? Unless you're flipping between them quite regularly, you're obviously not that confident it's going to work. And then there's simple things like power outages, but the scariest thing, and the main reason why we as developers should never let our solutions go to production in a single data center is these things. These guys are here, right? They do terrible things in data centers. They go in and upgrade, and really they break, turn things off, they pull power plugs out. But I'm kind of joking here, but if you're in a single data center, you will have some downtime. So we deployed to 2 data centers, but that makes things harder because most databases are not designed to run in 2 data centers, okay? And in this diagram here, the kind of elephant in the room is the database, because most companies I've worked at, if they're not active, they're not active because they can't run their database in a mechanism. They're too scared of sticking with like ACID and consistency and transactions, and they can't run their database with transactions if they run it active. So at that point, they basically choose, we're going to have some downtime at some point, okay? But we're going to be consistent, and that's fine as long as you're making that choice and not accidentally making that choice. So how do we make databases highly available? How do we make them handle node failure and rack failure and entire data centers going down? So most relational databases, most traditional databases run in a way which is either called like master slave or it's called primary secondary. And what we mean by this is that we run one of our database nodes as the special node. It carries on functioning as our normal one database server, our precious database server. But the database providers put in something which means that when you're writing to it, you can somehow either asynchronously or synchronously replicate to different versions of that database. Why on earth would you want to do this? In case the primary goes down. And then normally you have some type of like leader election, some way to make one of these guys be the master again. So that you will have a little bit of downtime because there's a failover process, okay? But you'll be back up in between 1 minute and a day. And what you can often do here is scale reads as well, because what these databases allow you to do is allow people to read from the secondaries. They don't allow you to write to the secondaries because suddenly then you break consistency and you have to redesign your database to handle writes for the same piece of data on every node. And there's a big advantage of this. And it's got one place to do writes. So it's super easy to, like, keep our normal ACID constraint. It's got one disadvantage as well. It's a single place you're writing. So it generally becomes very hard to scale. That becomes a bottleneck. And obviously the process for failing over normally will result in some problems. And if you've ever used, especially open source things, if they've got a mechanism for a leader election, that's normally the thing that goes wrong. Okay? So what's the alternative? So the alternative is some kind of peer-to-peer system. Anyone who doesn't pay for their music, etc., uses a peer-to-peer system quite regularly. But it basically means that we don't have a master. We don't have a node that you have to go to. Okay? So I, as like an application, can connect to any node in the database, and I can do read and writes. That sounds fantastic. Ops people in generally love it because there's only one thing to deploy. Just throw one more server at it. It's easy. You don't have this special, master node, which if that goes down, all hell breaks loose. You've just got one thing. And when you want more of it, you have more of it, okay? But the real downside to it, and the things that makes it quite hard, is maintaining consistency. Because over here, this point doesn't work on a TV, but I'll keep pointing. Over here, someone could be writing to Chris, and over here, someone could be writing to Chris. So how do you handle conflicts, okay? How do you make sure that you don't lose rights? And normally when people start talking about master-slave versus peer-to-peer, they start talking about CAP theorem. Who is familiar with CAP theorem? Maybe you've probably not heard of it since university or since you've been doing lots of reading on distributed databases. There's 2 times it comes up, okay? And it normally means, it's a way of reasoning, as a software developer, it's a way of us like say, what are we giving up and what are we gaining? And there's 3 parts to it. They basically say that you can only have 2 of these. Yeah. What's availability? Availability means that me as a client, your application, if I can connect to a node in the database and I can issue a read or a write, the database is going to say yeah and do it. Right? It's not going to say no. It's not going to block me. It's for ages. It's not going to say sorry. I might not keep that consistent. It's just going to do it. It's uptime. Okay. And then we've got consistency. So what we don't mean exactly what C means in ACID. But what we essentially means is every node in this distributed system that we're talking about agrees on what the data is. So if you go to node A, it's going to give you the same answer for Chris as node B. You're not going to get different ones. And you're not going to go back in time. You're not going to read Chris version 3, come back a minute later, and then read Chris version 2. And then we've got partitioning. What we mean by partitioning is, okay, let's say all the nodes are up. There's no nodes going down. There's no hardware failure, no hurricanes, no floods. But it doesn't mean that the nodes might not lose connectivity with each other. Okay, that could be the normal one people talk about, which is network partitions. When your 2 data centers lose connectivity briefly. But it could be as simple as it's any time in which a node can't communicate with another one. So that node could just be garbage collecting for 15 seconds if you've been experienced with large Java applications. There are many reasons why nodes can't talk to each other. And what databases and distributed systems often do, they either carry on or they stop. And why would you stop? And that's because as soon as you've lost connectivity with some of these nodes in a distributed system, you can't guarantee consistency. Because on one of these other nodes, someone else might be doing it right. Okay? I've whacked in some databases here, but it's always ready for an argument. Because most databases you can tune and run in different modes, okay, and move them around. And none of these are binary. They're normally a scale. When you use this technology in this particular way, you'll get this much availability, okay? So it's oversimplified. And when I'm building applications, I normally don't really care about the difference between this and this. Because normally if you pick availability and the ability to handle partitions, I just think that's like uptime. Okay, but you may lose some consistency, or you're picking in type of failures, be it node failures, network partitions. You're choosing downtime rather than people getting the incorrect result. And I very rarely talk about this stuff when I'm developing code. I don't know if anyone else has. Probably not, given how few hands came up. But normally, what people argue about in distributed systems and spend all the time talking about around the water cooler is how much latency are you willing to give up for consistency, okay? Because if I'm building SkyGo and I want to make sure that the position of what you're in inside Game of Thrones never goes back a bit, right? I would need to write to all 20 or 30 database nodes that we have, which has replicated that. Okay, I need to make sure they're all consistent. Okay, and that might take, some of these nodes are in Europe, some of them are in America. They're all spread around the world for fault tolerance. So it'd probably take around 5 seconds. Okay, to stop you going back 100 milliseconds because that one update was lost. So that's normally the kind of arguments I'm having. I'm like, I would rather someone go back a few milliseconds when they move from their iPhone to their computer than slow down every single one of their requests. And I've forgotten the guy's name actually, but someone wrote a really good blog on this. And they basically say, if stuff's going wrong, if nodes are blowing up and the hurricanes have hit, or there's just an ops guy pulling out some cables, then your trade-off is normally consistency, correctness, okay, versus availability. You get to pick application up with maybe slightly incorrect results, or application down. You pick, okay? Otherwise, it's solely, we're talking about latency and consistency. We're talking about how long are we willing to wait? How long are we going to make for a web page refresh, okay? So that's enough theory. I didn't want to pull you back to university days. Let's talk about Cassandra. Have some water. Do I have any questions on that before I move on to Cassandra specifics? No, all makes sense? You all dislike latency, right? You don't want websites to take longer. So Cassandra's used for pretty much everything. I'd be surprised if anyone has not used Cassandra today. Okay? If you use SkyGo, you've used Cassandra. If you play online games, most of them, a lot of them, sorry, are backed by Cassandra because they're all distributed around the world. And one of Cassandra's big use cases is multi-data center replication, which we're going to talk about. Anytime you use your iPhone. So if you want to go and see some videos about the latest Cassandra conference, one of the biggest wows was Apple's talk. So pretty much every time you use an iPhone, you're using Cassandra. They have over 75,000 nodes in production. Netflix is fully backed by Cassandra and contribute back to the project a lot. Lots of websites, Spotify recommendations for music, all those type of things is Cassandra. But the way it's gaining a lot of traction at the moment is anything to do with time series. Because as we're going to learn a bit today is with Cassandra, you get to pick the order in which Cassandra stores data on disk, which means if you want to get slices of ordered data, DVA is trying to make it work. We wanted tens and tens of thousands of writes per second, durable writes per second to disk across multiple nodes. Okay, and eventually we wanted to be able to do analytics on top of our production online database without extracting it and putting it in Hadoop. Okay, so we'll talk about how we do that later. So now we're going to learn about the internals, because one of the reasons I got into Cassandra, one of the reasons I know it's an open source project, but it's a very big open source project. And if someone says, go and look at the code, it's all open, then go for it, by all means. If you want to look at tens and if not hundreds of thousands of lines of code and try and interpret it. But there's a lot of content online about why Cassandra is fast, not that it is fast, okay? So let's go into it. So most people, when they introduce you to Cassandra, I remember reading this stuff when I was getting into it, tell you two things, and they expect that's it, that's all they tell you, we're done now. It's Dynamo based and it's big table based. One's a paper by Amazon, one's a paper by Google. Okay, and then you're like, what does that mean? You know, they just say this. Okay, but what we're going to do today, especially, is have a deep dive into what it means to be a Dynamo database. Okay, so by the end of it, you'll be able to impress your friends at the pub and talk about Dynamo databases. Okay, but essentially it's masterless and it's peer-to-peer. Every single node is equal. You can talk to any node, and every single node is data center aware. It knows what rack it's in inside your data center, and it knows what data center it's in, and it makes decisions based off that. And it means that if you want to do like replication across data centers, you don't actually need to do any work into it. It will just work. Then it's just a matter of, trading off latency versus consistency. Because if your data centers are next to each other, you're going to get some latency if you want to do consistent writes. I've touched on this. It's analytics. You can lie to Cassandra. You don't have to be in a different data center. You can just say it's in a different data center and call it analytics. And the great big advantage of that is you can segregate nodes, right? You can make sure your website only talks to the orange ones, and you can make sure that your big analytics job only talks to the blue ones. And the asynchronously replicate to each other. Well, normally the data would come into the online one and asynchronously replicate to this one. But it means that you don't suddenly need a whole new department. We have a whole new department, this guy, which basically I took out the data every day and put it into HDFS and then ran Hadoop on it to do like the analytics, like to say, how do we get people to watch more Game of Thrones and less EastEnders, that type of thing. So it's a paper. I would go and read it. It is actually, it's not a hard paper to read because it's practical. It's about the system that Amazon built to back your shopping store. I'm sure everyone uses Amazon, right? Everyone uses the basket. Use the basket, you use Dynamo, okay? That's what it was made for. They basically decided that normal databases don't work if you want 100% uptime, okay? And the basket system being down surprisingly made that Amazon lost money. Who knew? There's lots of concepts in here. And we're going to go through them. I'm going to race through them now, just so you've got all like the names in your head. And then we're going to go through each of them and show how they're used in Cassandra and how it differs a bit from Dynamo. Because it isn't just like, that's the paper, we're doing that. It does differ a bit. So the first one is consistent hashing. Sounds fun. But essentially, if you have a 1,000-node database cluster, which people do, okay? We test, DataStax takes Cassandra and tests 1,000-node clusters every day, okay? You need to know where to go to get your data. You can't do a full table scan. It's bad in a relational database sitting on one node. Think what it's like doing it on 1,000 nodes. That's just, not many people have 1,000-node clusters. Most people have 10-node clusters, 5-node clusters. It's still bad, right? They might have a terabyte each, and you don't want to do a full table scan across 5 nodes. Okay. So consistent hashing is about working out, possibly even the client, where the data should be and going directly there. Okay. Then the storage engine, which is not anything, that's just Cassandra, takes over and puts the same efficiency to working out exactly where in disk it's going to be. Then we've got replication. So there's no point having a distributed database with hundreds of nodes and then storing each piece of data once, okay? You've just taken like a big ball and made it into lots of little balls of mess, okay? The reason we're on many computers is because we want to replicate data, so we can tolerate failures and so that we can scale. And so we're going to talk about what strategies we use for that. And then we're going to talk about gossip, which just means that Cassandra is really social, it talks to each other a lot. But essentially, when you've got a big distributed system, it would be the same if you're building your application and you've got many nodes and they weren't stateless, they had to speak to each other. Cassandra needs to speak to each other a lot because you can throw new nodes at Cassandra, you can scale it up, you can scale it down, and they need to know that and move the data around to make sure it's still meeting your application. And then we've got the ways, when things go wrong, you need a way of fixing yourself, okay? When we lose writes because nodes are down, because the network's down. Cassandra has a couple of mechanisms, or Dynamo, sorry, mentioned 2 mechanisms for sorting that. One is basically help your buddy out, which is like, oh, if he's down and a write comes to me and it's for him, not me, I'll just keep hold of it for a bit and wait for him to come back up. But if that fails because he's down for too long and my pocket fills up, then you have to run this thing called a repair, which basically says, go and talk to your friends and make sure your data is consistent, okay? And there's a couple of things which Cassandra is not. So if you go and read that paper and think, oh, Cassandra is a key value store, because that's what baskets required, right? You just need to go customer ID, get. But Cassandra didn't pick the data model of Dynamo, which means it chose not to do vector clocks. And vector clocks are just a way of, when we're talking about that scenario where the same thing's been written on the other side of the world, vector clocks are a mechanism for working out if that's happened. But we're not going to go into those because Cassandra isn't implemented. So, picking the right nodes. This is consistent hashing. And it's pretty obvious that we don't want to do a full table scan across 1,000 nodes. Okay? So how are we going to solve that? Let's have a look. So this is some data. Looks like relational data, right? It's a table. It's fine. It's nice and easy. A data in Cassandra has a partition key, or it's got a primary key. A really special part of that primary key is the partition key. And what we do is we hash that and turn it into a big number. We don't stop there. Each node inside a Cassandra cluster owns a range of these numbers. Okay, it's not a master for it. We'll talk about that. I'll beat you up later and hit you with a stick if you say it's a master for it. It's not a master. It's just one of the replicas. Okay. So remember, we're going to take Jim, we're going to hash it, and then we can work out which node has it. And that's how every single node in a Cassandra cluster can work out where to forward a write to. But it's also where the clients can. So you can use your driver and say, make sure you go to the right node. Okay. And we can see that as a picture as well. So if this guy, so we see here that node B owns all of these, and node C owns all of these. Okay, it's exactly the same information as there. I just put it in a big round picture, and that's where our data ends up. But it's not very fault tolerant, right? Our distributed database isn't doing so well yet because we've only got one copy of each data. If we were to lose node A, and sometimes you might think I'm scaremongering, right? How often do you lose your servers? Like, you've got thousands of servers very often, but even if you've got 6 servers, but I don't just mean hardware failure. I don't mean, hurricanes. I mean an operating system patch. I mean upgrading to a new point release of Cassandra with a bug fix you want. Any reason to turn it off, any maintenance, okay? You might just be decommissioning some old hard drives, some old hardware, okay? So think anytime you want to turn a server off, okay? So we want to make sure that we don't lose Johnny and Jim if node A and B go down, okay? So we need to replicate it. So Cassandra has 2 types of strategies, one you should use and one you shouldn't, okay? Simple is just, it's for your dev station. It's so you don't need to configure your nodes with what data center and rack they're in, that type of things. It's like easy get going if you want to. Don't go to production with that. It's just for like bootstrapping and playing with it for the first time. You've got network topology. The only real difference between, from your point of view, is with network topology, you need to kind of tell each node what data center it's in and what rack it's on, so it can make good decisions about where to place your data. And assuming that you tell Cassandra the right things, it's never ever going to put 2 copies of Jim or John or whoever had in Johnny on the same rack in a data center. Does everyone know what I mean by rack? So in a server, you'd have a big server farm, and they'd be in racks, and each rack would have its own power supply. Okay, so that is, if the guy in the red shirt comes by and kicks one power supply out, he might take out an entire rack. So if you've distributed your data and replicated it across 3 computers on that rack, and he's killed them all, they've all fried because for some reason that did kill them. So Cassandra wants to not put the data, more than 1 copy of your data on the same rack. Unfortunately, if you do have more replicas, you pick how many replicas, by the way. You might want 1, 3, or 100 if you're really paranoid. If you have more replicas than number of racks, then it can't spawn racks. It will then put multiple copies on the same one. So let's see how that would work. We're going to assume that the client's going to connect to one of the replicas, okay? So he's going to do that. I spent ages on the animation, okay? So expect some flaws. All right. So a client, okay? He talks to a node. It can be any node, but we're going to assume it's one of the right nodes because the clients can do that if they want, because they can work it out the same way that the server nodes do. We haven't talked about configurable consistency yet, but pretend I have. This is a consistency level of 1, which unsurprisingly means I'm going to get it onto 1 disk before I tell you your write is durable. Okay? So he's going to return right away. Done. Right? But that's not where it stops. Okay? This node here will then, after a replication factor of 3, he's going to find out which nodes do it. And he does that by finding nodes which are on different racks to itself, but in the same data center. So he's found these 2. Okay? But that's a deterministic algorithm. Nodes don't move around. And if they do, they gossip to each other and tell everyone they've moved around, so that everyone knows that you need to go somewhere else. But we've also got another data center because we're really paranoid about a flood. But Cassandra doesn't copy the data over 3 times because it's assuming that this network link here is slow or expensive or something. So what the coordinator does then is he designates a remote coordinator in the other data center, and he sends it once, and then he then does the exact same thing in that data center. He becomes the coordinator of that write request in that single data center. And then we're done. Any questions on that? I'm going to talk about the consistency next, because what we've done here by selecting a consistency level of 1 is we've asked for lowest latency possible. Okay, there's actually even one less than that if you want, but we'll talk about that later. So I want to remind people here now, because the question I got, I only given this presentation once before, and the question I got after was, what happens if the the node it hashes to? What happens if that's down? Does it all stop working? And the answer is no, right? We pick 3 replicas by hashing it, picking one, yeah? And then we use a deterministic algorithm to pick the other 2. Let's say we've got a replication factor of 3. But you don't ask that master, the one it hashes to, what the other 2 are. Anyone can work that out. It's a deterministic algorithm. The client can work that out. And you can talk to any of them. I'm going to talk about load balances policies in a bit, about which one you choose to talk to. But there's no special node. There's no one thing you can take out in a Cassandra cluster, apart from the planet, which would mean it go down. So just remember that, okay? But then, how safe do you want to be? What happens in the previous scenario if the hard drive went down of that node we wrote it to, after we've acknowledged to the client, but before we managed to get the asynchronous replications out? You would lose the data, right? Because it's gone, the hard drive's gone. So you have to decide as application developers, and this is where working with a database like Cassandra pushes more complexity back into us, because when you've got full asset guarantees and you're running your single node of your database on a server, which is the highest spec hardware that you can get and dies once every 10 years, you can go through your whole career without ever having your database server die, okay? But when you're deploying it to tens of commodity, cheaper hardware across the entire world, it'll happen regularly. So we've got to think about this. And the way you do this is you basically pick latency or consistency, yeah? So if you want to write it at 1, we've already discussed that. There's also 2, there's also 3. But then you're more likely to use things like quorum. Quorum just means a majority. So if you've got a replication factor of 3, and you write to a quorum, which gets it to at least 2, still writes it to all 3, but it only waits for 2 acknowledgements back from the other nodes. And you read it at quorum, which is a majority. It means you need to consult at least a majority of the replicas before you come back with the response. Then you're going to be consistent, because there's always going to be a 1 overlap. And the other thing that you often want to do is avoid ever jumping across the data centers. Because if one of them's in the US and one of them's in the EU, it's going to be at least 120 milliseconds or so just in speed of light, okay? So there's lots of things called local quorums. And that basically says ignore the other data center. I'm talking to this data center right in front of me, and there's 3 replicas here, and I'm going to wait until 2 of those, a majority of those. I don't care about the other data center. Okay, just get it over there when you can. And it'll do it as quick as light if there's no problems going on. So we go back to our scenario that I had at the start of my very oversimplified architecture diagram that any enterprise level architect would kill me for producing. We're now in 2 data centers, but we've replaced our single point of failure, our single silver blob, with lots of Cassandra nodes, okay? And what we do is we make sure that the applications in this data center only talk to these nodes. And then we make sure these other ones only talk to these nodes. And you can do that with load balancing. So never put a load balancer in front of Cassandra, okay? Remember that, never put a load balancer in front of Cassandra. It's all built into the drivers, okay? The drivers know how to do this. So you can tell your driver, only talk to nodes in data center Europe, unless Europe's gone, unless the data center's died, okay? Then you can go over to the US. So it'll be a bit slower, but it means your application will still work. Token aware is that fancy one I was talking about, where the actual client does the hashing too and does the algorithm and make sure he speaks to a particular replica. So you make sure you don't do an unnecessary network hop. But then you have other ones like latency aware. So this is where the drivers keep track of who are the fast nodes and who are the slow nodes. You know, if for some reason you've got a hotspot in your data set, so a couple of the replicas are a bit busier, then you talk to the other nodes, use those as coordinators, and then the guys who are busy with, Chris, the popular piece of data, then all they have to do is storage, retrieval. They don't need to do the network communication and the async replication. And the great thing about this is when, I don't know, someone likes Mongo, so they turn off all the Cassandra nodes to create some crazy scenario, these nodes here can just fail over to the data center, okay? And if your application goes down, remember by down, I do just mean perhaps you're just doing a release.
but you don't want any downtime. Your clients can fail over to your other data center, but in the background, all of the data that's going on, all of the writes and the reads are still getting replicated to your other data center. So when it comes back, then you're all good. And then, yeah, that's really bad. Data center just goes away. That's what happened to me when the data center flooded. So what happens when Arnie comes back? So you've seen the Terminator. Anyone? It's an old film. But essentially, normally, everything goes to pot when Arnie comes back, but not so much with Cassandra. So you kind of get a few hours for free. That's what I always say. Cassandra will self-heal if nodes and things have gone wrong for up to a configurable amount of time. Default's 3 hours. And it does that by basically, this was all mentioned in the Dynamo paper, of keeping hints, okay? Let's say that a couple of replicas are down for a piece of data to Chris, all right? So the writes are going into the other nodes. What you can do is you can say Cassandra will keep hold of those writes, okay? As long as it meets your consistency level. If you've done all or quorum, then it's going to say no, there's too many nodes done. And then when these two come back up and everyone finds out about it, those writes will be sent to it. But it doesn't do this indefinitely, because eventually that would just be a classic Java memory leak where you just fill up a map, you fill up a bucket, okay? So it keeps them for around 3 hours, after which point you need to do some manual intervention. When you bring those nodes back up, you basically tell the new nodes, you're probably broken, go and fix yourself. And it goes and talks to all of its peers, and it compares the data and brings themselves back up to date. It doesn't stream the data over, don't worry. It basically takes a Merkle tree, which is like a tree of hashes, and tries to work out without sending the data back and forth whether there's any differences. And then if there are any differences, it sends the data to the node that's been down. There's a fancy diagram for it. See, there's no Cassandra users here. There's repairs improved vastly with Cassandra 2.1. But if you haven't had the pain of repairing Cassandra 1.2, then you're not going to be interested. So we've talked about this lots. And there's always a hard way to explain lots of the concepts in Dynamo because they all depend on each other. You can't have easy scalability by adding nodes without gossip. And gossip's a thing which basically means that all of the nodes in the cluster know which nodes are down, they know which nodes are up, and they know when new nodes are added, and they also give all that information to the client so they can do the algorithm. And so basically gossip is just I think the exact specifics are every 1 second, a node talks to 3 peers and asks them the state of all the peers. And then they kind of see who agrees and that type of thing. So you can go onto Cassandra, you can go in the command line, you can say who's up, who's down to any of the nodes, and they can tell you about all of the nodes. So scaling. So as I said, a lot of people use Cassandra because they want for non-functional requirements. They don't really want a map of maps. They don't really want some time series data model, okay? They actually just want to be able to have linear scalability. What do I mean by that? I essentially mean, if you've got one piece of hardware, one computer, there's 10,000 transactions a second. We do 10,000 writes to our database. If you add 2, you should get 20,000. But has anyone actually built a piece of software which does that? It's kind of hard, okay? And if there's any kind of shared state or shared anything, it's extremely hard. But because Cassandra has no master, and as you add more nodes, they just basically come into the cluster and say, oh, it takes a little bit of data off every single node. So they all got a bit less to do. So you can keep on adding nodes to a Cassandra cluster. And this is actually a server, like an experiment which Netflix did. So they're one of the biggest users. They talk lots about how they use Cassandra. But they basically started off in AWS. Everyone know AWS is? Just provisioning virtual machines. So you could recreate this with known things. And there's a big blog article in the Netflix tech blog where they just started off, with a small number of nodes. And they basically, over the course of a few hours, just kept on adding nodes and kept on loading it just to see what would happen. And eventually they stopped when they got to 1 million writes a second. So they scaled it up to about 300 Cassandra nodes. They cost about 300. And then they were writing these at quorum, I believe. And then to stop there, if you're interested in this kind of stuff and you go and read the article, they then decided to start randomly killing nodes to see how the throughput was affected. And they got it down to losing 1/3 of the nodes. Because if you've deployed things to AWS before, you probably know about availability zones. And you can treat those as racks, which means that you can, if you ask for a replication factor of 3 and you deploy it in Europe, and you say you've got 3 availability zones, you can make sure that each piece of data is actually as a copy in each availability zone. So you can actually lose 2 availability zones and not lose any data. So go and read about that. That's fun.
So what do you have to pay for all of this wonderfulness? Let's stop on questions. So covered quite a lot there. Any questions come up? How are you going to live without perfect consistency? Anyone? You're not going to use Cassandra, eh? So,
sorry.
Yeah, go.
In terms of knowing which data is the latest, is it just machine time?
Correct. So,
Because have you?
conflict resolution. That's what vector clocks were for in Dynamo. I'm not going to go into those, but essentially, because it was a key value, if you say red, then write the value back, it's one blob. So if you get it wrong, you lose the whole thing. Cassandra is a wide column map of maps. So you have really, really, really long things. So if I'm storing financial data, I would be putting the key of that map as the time. So I'm never actually overwriting the data, if that makes sense. Which means that you very rarely do reads and writes in Cassandra data modeling. But you're right, if you are doing reads and writes and you are doing updating the same value, it's last write wins. But it's on the column, it's not on the key. So you wouldn't lose everything about Johnny, you would lose his an update for his name. Does that make sense?
Yeah, wasn't the question I was asking.
Oh, sorry.
No, it's more about the catch up for when you've lost a node.
Oh, sorry, yeah.
Is it just is it machine time for replication for which is the actual right data?
Correct,
Same
yeah.
key.
So every single piece of data that's written in Cassandra down to the column level, because you don't have to update an entire row at once, does have a timestamp of when it's written.
Yeah.
The client can inject that or the server can inject that. It's up to you. Normally the server does. So if you've got 3 replicas, one of them dies and you rebuild it, it will take the data from, it would actually pick a node to rebuild from, like during that bootstrap process, and then you run a repair and it would then make sure that the latest version of that piece of data was
Right,
on all
but
3.
that's determined by the machine.
Yeah,
clock.
exactly.
So you've got them synced up.
Yeah, you have to have, yeah.
Something like Amazon Basket concentrate more on having more latency, maybe over consistency.
So if you read the paper, because they actually talk about that, they talk about their business in the paper, is they would rather, they wouldn't necessarily pick, they would always pick availability. So if we go back to like the CAP theorem, availability is number 1.
Yeah.
And then probably latency, and then probably consistency. And the way they do their merges is they'll annoy some customers by this, but they never ever want to miss like a basket update add. Okay, so like by default strategy would be to merge. This is why they use vector clocks, so they can, like, if they have 2 conflicting updates, rather than work out which is right, they just merge them by everything in the basket.
Oh, right, okay. Yeah, that's easy.
Yeah, but they do have ways of like doing it. So if something ever just appears extra in your basket that you thought you deleted, you know why. So, yeah, go.
And how do you group data? Sometimes you need to take information from all the nodes, like counting, votes, or things like that.
Correct. So you need to, we're going to talk about this in the data modeling section. So you want to make sure, we talked about, remember that thing that we hash? We call that the partition key. You want basically always, unless you're doing an analytics job, you know, like some kind of like thing you're happy to take some seconds rather than milliseconds, you always want what you're going to read to be in a single partition. Now, a partition can be very big, okay? So it can be up to 2 gigabytes and up to, I believe, 2 billion columns. So when you think of like a row inside a SQL database, you might think of like Chris, right? And you'd have a primary key of, say, just my name. In Cassandra, what you would do is have the primary key made of, say, my name and, I don't know, let's say you want to do what you said on all the employees for a company, okay? So you would make the partition key, you know, Chris and the company, so that all of the employees for the same company would be in that one row, in that 1, 2 billion. So you could query it from one node or one of the replicas for that node. And then, of course, that might get too big. You might end up with lots of events for these employees. So then you can bucket it. You can say the partition key is Chris, data stacks, Monday, the 19th of January. So all of the events for that happen on one node. It might make more sense when we talk about that. I've got some diagrams around this. But if you end up with wanting to query multiple partitions, okay, that particular part of the primary key, then we need to talk about how you data modeling and maybe change it. For analytics jobs, you are typically doing a full table scan, but that's the kind of thing you're doing at the end of the day normally to recommendations and working out how to make people watch more Game of Thrones, that type of stuff. I'll try and hopefully cover some of that in this section, because this is the price you're paying for moving to a database, which is going to mean you don't have to have downtime during releases, that you can scale it, all those type of things. First thing, I often joke with people, the best way to think about data modeling in a distributed database, okay, is forget you went to university, forget you ever read anything about data modeling, pretend actually, if you've got children of about 5, 6 year olds, get them to do it, and they'll come up with a better, I swear, they'll come up with a better version than you will, because you'll overthink it and you'll try and denormalize and those type of things. To which people are like, no, we get really stressed, because that's what we know how to do, okay? That's why we've got Hibernate, we've got all these object mappers, we've got entities inside languages, This is a scary concept. We're going to change it. So they normally make people calm down a little bit, okay? And then this one really gets people, because this is like the anti of good data modeling in SQL databases. We just want to do query-based modeling. A lot of the time you might have done this, right, for optimization. So you've denormalized in a relational database, created materialized views so that you don't actually have to do those big crazy joins, every time someone reloads your website. So you may have done some of this, but we're just going to do this from the start. And they get really scared as well. So that's the bad news. The good news is that the language you're going to use to do it in is really familiar. So once you've worked out what to do, we just replace the C with an S. This wasn't always the case. If you use Cassandra, when I started using Cassandra, there was a completely different way of interacting with it. And it was scary, and it was so different. So not only did you have to change how you're going to model your data, you need to learn a whole new tool. It wasn't JSON, because that was nice, but it's just a completely different query language. But not anymore. You guys, if you've never used Cassandra, you don't have to worry about the old way of interacting with it. It now has a very SQL-like thing. And this shouldn't scare you, okay? The denormalization will scare you, but create table scores, something like that's not going to scare you, right? We've all seen stuff like that. And we can insert into them, and we can select from them. There's lots of limitations. You can't suddenly just do everything that you could do in SQL, because it's not going to let you do things that don't make sense in a distributed database, okay? We've got quite a lot of types. Don't worry, you don't have to memorize them all. There will not be a test on Cassandra types at the end of this. Most of them you're used to, right? There's things like varchar, but actually you don't need to tell it how many fields it is. So you're no longer going to have to type varchar 256 all the time. Your fingers aren't going to have to write that anymore. And does anyone know why you have to give it a number in relational databases?
Maximum length.
Yeah, and it stores it on disk like that. So if you put Chris in your varchar 256, it's still using 256 bytes on the disk, okay? Cassandra doesn't do that. It just stores it exactly. If you miss out a column, you don't store a column, it doesn't store it on disk. So it'll end up using a lot less disk space until you replicate it 3 times. We're going to have a look at a few of these types, because some of these types you will not be familiar with, or well, you will in programming, but you won't in a database, okay? And they're going to encourage you to denormalize, okay? So before we move on to the denormalization side, let's have a look at the UUID. This is just go use this all the time, Cassandra, okay? We're no longer going to create sequences. We're never going to use the term auto increment in a distributed database, because how do you work out what the next value is? We talk to all nodes, okay? So people use a lot of unique IDs in Cassandra, okay? Normally generated on the client side. And then, of course, one of the variations of a unique ID is a time UID, which actually has a timer. So remember I talked about how Cassandra can order disk and is very good for time series. This is one of the main reasons why, okay? Because we're going to say, you pick a partition key. I'm probably going a bit ahead of myself here. That decides what nodes it's in. Then you pick these other parts of your primary key, and that decides what order they are on disk, okay? So you can use time UIDs to both make your value unique and decide that you want your customer events or your employee updates in your employee database to be stored in order. So if you wanted to query them all in one go, you seek once on a disk, and then you read it all out without doing multiple disk seeks for a query. And if you haven't, does anyone know how long a disk seek takes on a spinning disk? It's around, about 10 milliseconds. So if you have to do a join, or you have to talk to multiple, you have to do multiple disk seeks. Let's say you have to do 10 of them. You're going to have 100 millisecond queries, whereas what we're aiming for in Cassandra is on spinning disks, we want single-digit millisecond queries,
Okay, and I can show you how we can do that, even though one disk seek can take 10 milliseconds, and we always get things from disk. And if we're on SSDs, we want sub-millisecond queries, okay? And we want tens of thousands per medium-sized computer. But these are the types of things in Cassandra which you won't be used to if you're used to using relational databases. These are the kind of things which are going to help you denormalize, okay? They're going to make you duplicate your data, okay? We're going to do an example, and it's videos. I'm sure you remember where I last worked, where I got this from. But essentially, we store lots of video information, and we've got some extra things in here, right? We've actually got a set, so you can have a set in Cassandra. And then the good thing about sets is they're idempotent. You can just like put loads in. It doesn't matter if you get duplicates. And we've got maps. Okay, so we can store key value stores inside our thing. So if you've looked at other NoSQL databases and you're used to schemaless, that's not Cassandra. Cassandra is a very schema-orientated database. But then you can put maps in things. So you can sneak in your non-schema if you want, or if you're really crazy, you can put lots of JSON fields in it, because people do that a lot. And then we've got user-defined types. So let's say you're sick of having 40. Let's say if you like types and statically typed languages, you probably don't like 15 maps inside your type inside your database. So you can actually give things names. So we can have an address and we can group types together. And then if we want, we can put them inside maps, or as I said. So for a particular video, a bit of content you might watch on television, via something like Sky Go and Netflix, they'll have tens of different copies of that content, right? One for an iPhone, different size screens, different bandwidths, all those type of things. So we can have a set of the video metadata, which might include, what type of video it is. So they're the kind of things which are going to help you denormalize, get out of this, go into this crazy world. And you can go really crazy if you want. You can take that crazy JSON format which people gave you, and you can create all the types if you want. Okay, now you don't have to. You can store JSON inside unlimited text fields in Cassandra. But if you're actually wanting to see it in the database and see it in your query language, then this is how you do it. Tuple. I don't know what you use a tuple for, to be honest. I don't know. Maybe coordinates? Yeah. Oh, well. Anything for a tuple, I think why using user-defined type, you can give things names. But hey, if you just want a tuple and it makes sense for you, go for it. Counters. Someone actually already asked me about this. Counters, they were added. Cassandra's open source. We've talked about that, right? You know what open source means? People can add code. Okay, it's not necessarily got the best review process. And at one point, something called counters, and it was for a particular company, and they basically, there was lots of issues with counters, especially if you had down nodes. Because we can talk a bit more in detail about how Cassandra does like replay of a commit log, and it basically meant you could do double count counters. And there's a real joke that DataStax, which are the company, they about, I don't know what the numbers are, but a lot of the Cassandra committers work for DataStax. And they raised a big load of money recently, and someone did joke that the reason they'd raised £106 million was to basically make them work. And they did. So in Cassandra 2.1, all of those issues that you'll get if you Google it on Cassandra counters are no longer there. And Cassandra counters are really useful if you're going to store like statistics, okay? I wouldn't use counters to bill someone, because if you're, let's say you, I don't know, Spotify, you're keeping how many times someone's played a piece of music, yeah? And you're going to basically say to the people who own the music, we're going to pay you $15 because they played it 4 times. I wouldn't use counters for that, because you can't work out, you can't go back to the original data. But if you're going to keep like website hits, or how many times people have played a movie or watched Game of Thrones or something like that, they're really good. This is a really interesting thing. Who here has a like some kind of like cron job that runs in the background that goes and cleans up old entries, old trades, or old things inside the relational database? Well, you don't need to do that in Cassandra, and it's really important in Cassandra because people put billions of like pieces of data in it around, time series data. If you had to go and clean them up, etc., then it would be a pain. So you can just set a time to live. That basically says after this long. And I tend to use the command line, but if you want, if you've been in like SQL developer, those type of things, there's a very similar thing for Cassandra that will connect to your Cassandra clusters, see the schemas, those type of things. Exciting. But let's have a look at an example. And this is an example which I pretty much built for Sky, but changed lots of things to make sure it didn't look exactly the same. So we have a requirement, right? We need to store some customer events. A few reasons. We need to be able to like query them to see what a customer's been up to, like a call center. And we also need to be able to do some analytics on them, okay?
We're going to talk more about, and I classify the first as like my operational application. It's going to be like a web app which queries it, and so when I ring up and say I can't play, the Man United versus Chelsea, they'll be like, oh well, you've got your password. There'll be an event in there saying, you've incorrectly entered your password 16 times. So we have things like an event type, where it's come from. Has it come from a phone? Has it come from a website? That type of thing, and the time when it happened. And then we've got a bit of extra data called tags. And we want to be able to get all the events. We want to be able to get those time slices, those type of things. So let's see how we do that in Java. That's how we do it. So we've got one of these tables we're going to put customer events in. Yeah. The only thing you can go wrong with in Cassandra is picking a bad primary key. The primary key gives you control over everything in Cassandra. So you have the first set of parentheses, right? And that's the partition key. And you can put as many fields in here as you want. Okay? So we could have put extra things in here like stuff ID. But what I'm basically telling Cassandra here is when I do my queries, I'm always going to be providing you a customer ID. And that means that Cassandra can go directly to a node where the data is and get it off disk. Yeah? We're not going to be looking around lots and lots of nodes in our distributed cluster. And then we've got the extra parts. The extra parts are where you get to pick how Cassandra orders it on disk. So when you come to query multiple of them, so we want multiple of events for the same customer, we don't suddenly start darting around the file. We go to the file, we read it out. Or if it's been cached, etc. It could be, you know what I mean? And this is what it looks like to you, to developers. We're used to this, right? We're used to tables. We understand this, yeah? And I'm going to show you some Java code that interacts with Cassandra, but it looks just like JDBC and all of the database code here. It's really boring. But what's really important is to understand about how it maps to the on-disk format. So even though we've got 6 rows here, okay, how many partitions have we got? It's an audience question. How many different nodes will this data be stored on? 2. Why is that? Because we go back to our primary key. It's customer ID, right? And we've only got 2 distinct customer IDs, Charles and CH Batey. Okay? And then what else was in our primary key? We had the time. So that's picking how it's ordered on disk. Okay? So these kind of 6 rows here actually turn into 2 rows on Cassandra on disk. Okay? And some of the information's gone. Well, it's gone kind of. So the real key, the partition key, is where Cassandra jumps in. And then all of these events are stored in order of here. So if we ever wanted to like query slices of events, it's super efficient. Okay? Want to go through that again? That's why it's so good for time series. It's not rocket science. It stores it in the order you want it. If you want to query it in a different order, you store it twice. It's not magic. Okay? The only thing we have to do to make it possible is to make tens of thousands of concurrent writes a second possible. So you don't need to be scared of the 200 millisecond write, 300 millisecond write. So that's kind of SQL, right? That's kind of like your data modeling. That's the hardest part, even though there's only a few slides. Getting this right is the hardest part. And what people often do if they realize they've done it wrong is you can run kind of like batch jobs across your cluster and like take it out of one table and put it in another in a different way. Okay. Once you've picked that, actually writing some code to talk to it is trivial. It's not exciting. We'll show you anyway. So there's 2 kind of categories of drivers for Cassandra. There's ones which data stacks make, and then there's other ones. And the ones that data stacks make are nothing to do with products. Nothing. They are completely open source. They're on GitHub. They have non-data stacks employees committing to them. Okay. They're just data stacks is products are based on Cassandra, and thus they need lots of people to use Cassandra. So they employ a lot of people to go and commit to open source for Cassandra. The big advantage of these is they're always kept up to date. They're always released at the same time as different Cassandra versions. Another big advantage is they all have the same programming API. If you've worked with it, apart from obviously the differences, the certain differences of the languages, they're all going to look the same. They're all going to be configurable in the same way. They're all going to have the same kind of test suites, because when you come to write a driver for a distributed database, it's hard. Okay? You write a driver for a database server which sits on one node. You have one connection. It's not hard. If you have 1,000 nodes, if you have hundreds and thousands, an unlimited set of nodes you need to speak to, you need to load balance like queries across them, and each connection between the driver and the database node can handle over 128 concurrent queries going on at once. It's hard. So if you want to use like one of the other ones, by all means do, But I know these ones are very well tested and by far the most used. And the one I showed you was the DataStax Java one. Okay, and they're all in Maven Central. They're all on GitHub. You can go play with them. And here it is. So I proved you. Look, there's a GitHub page. It is open source, and it is in Maven. So it's not exciting. So everyone, Java 8, like Java 8. So basically, this is just you get a session object, and you can execute free-form strings if you want. It looks just the same. So as I said, the hard bit was working out how to put it in, not how to write the code. We have a map function which basically gets fields out of it and puts them inside, a custom kind of Java object called customer event. And the only reason I pulled out a map function is so I can use it for all of them. So we have prepared statements. Very similar concept to, your regular relational database. It's where we only send over the query once, and Cassandra can do any optimizations it can do for that query. Okay, so then you prepare it once. This is post construct. This example, the full working example is on GitHub. I can put a link to it. We prepare it once after the bean's constructed, and then every time we execute it, we just bind this customer ID. Okay, and remember the customer ID was the partition key, so that would be a really efficient query in Cassandra. If you don't like prepared statements and you don't like putting big strings inside your database code, then it's got a little builder. No, this is just personal preference, whether you want to use from this with this. The difference here is I've actually done a range query, just to show a different example. So it's basically we're using it is a UUID, remember, that made it unique. It's just greater than and less than, and then we do it exactly the same. We call get customers, and then we use the same mapping function. So again, nothing groundbreaking about that. Now, there is Spring Data, Cassandra. Does anyone use Spring Data with anything, like Mongo, relational databases, those type of things? Just a mapping API. It means you don't have to bother writing any of this stuff, essentially. You basically just create an object in your particular language, and then you say that object looks just like the database, make it so, and it makes it so. And the drivers for Cassandra have the same kind of thing. So you just tell it what the clustering columns are, whether that's order on disk, partition key, which node, and then just the extra fields. If the names are different to the variable names, you just put it in there. And then you just do an interface in Java. And then you put the queries on, and it generates the code at like deploy time. So you get to be lazy. And Java developers enjoy being lazy. They don't actually like writing code, so they normally like this kind of stuff. So you can do a few extra things with the mapping API. You can, even if you've got a string inside Cassandra, you can tell Java it's an enum. And obviously it will, assuming that your values are correct inside the database, it will map it into an enum. So to say store type, we didn't just want to store as a string, we like types. Then we can put that inside here, and Cassandra will just sort that out for you. And then how do we deal with these user-defined types? These crazy user-defined types, because we just make whatever we want. Then it is what you might imagine. You can just create Java classes which look exactly like them with the same field names, and then stick them inside your main object. So here, what have we got? It's there somewhere. Store, there we go. So rather than have 15 string fields on it, you can group them by name, which is store type. And then, we just add another one because we don't want to write code anymore. We're on the mapping API. Query tracing. So you'll do this, and eventually your queries will be really slow. And they'll be really slow because you're going to multiple partitions, probably. But if you don't want to worry about that, you can just turn on tracing, and it gives you get this little nice little output when your query is executed, and it actually tells you about chatting to all the nodes. And if you see it chatting to like every single node in your cluster, you need to rethink your schema. It's not the kind of thing we're interested too much in intro. It's the kind of thing you'd get into if you actually started using Cassandra. Any questions on interacting with Cassandra from the drivers?
Presumably, you can use any mapping API.
No, so it's not going to plug into something like Hibernate or something like that because they're all reliant on it being JDBC. Cassandra, there isn't a JDBC driver for. There is actually, but it's produced by someone else that's kind of not been maintained. Eventually, the DataStax driver will become, or there is plans to make it a JDBC. Then it might plug in, but you can only support a subset of SQL or different parts of SQL, so it's not necessarily going to work. But I always warn people off mapping APIs that are going to hide the Cassandra schema from you, because you need to really make sure you understand how it's stored on disk and how it's partitioned. So I would almost say don't hide it from you.
Like it might be trickier for existing applications to then any migration process to something
Absolutely.
like this
So
would mean?
are you normally starting again with your data modeling when you go into Cassandra? And most people who come to Cassandra have an existing application which they're porting because it's hit their scalability limits. So they're normally willing to put some effort in. Okay. So the other features, these are, I tried to find a pitch like break glass in case of emergency features, but I didn't have time. The Wi-Fi on the train didn't work because essentially there's some extra features in Cassandra which are anti-Cassandra, or I think they're like anti-Cassandra. They go to multiple partitions, they do crazy things. And it's for that 1% of your application where you don't, that might need to do it. You don't mind it being slow, but you also don't want to run two databases. Okay, so lightweight transactions. I don't like using the word transaction because distributed transactions are inherently going to be very slow. But all this basically is allowing you to do a couple of conditions on some inserts and updates. Okay, and so selecting usernames is the common example which everyone uses. Okay, updating a bank balance might be another one. Something which can't be wrong. And it's going to be a lot slower, and it's around 4 times slower when you actually put it into load test, because basically like all of the replicas need to kind of like stop what they're doing and agree on it, which is very anti-Cassandra because the idea is we're going to get ridiculous throughput because we're not going to do that. But if you need to do it for 1% of your application, it is there. If you use it for every single query, you probably pick the wrong database or the wrong data model. And batch statements, not for batch insert. This is for batch atomicity. So what you can do with Cassandra is say, here's a bunch of statements, make them all so, right? They're not isolated. Do not think ACID, okay? But what you can do is say, if this comes back as successful from your driver, Cassandra will make sure all of those 4 statements in here are going to be done at some point. Because it's not going to tell you it's going to do them until it's actually stored it on 3 nodes that it will do it, if that makes sense. Again, much slower, but for the times that you really don't want to have inconsistent data across tables, then it's for you. And you can combine the two. So you can put a little lightweight transaction at the end of a batch, but then you have to be on the same partition. So this one, not the same partitions, this one, the same partition. Again, 1% of your application for that little thing, so you don't need to then have another database sat there to do your more transactional stuff. Whew. Is that enough? I have like 50 more backup slides if you want. No, I'm joking. I do. So yeah, so you need a reason for picking Cassandra. That's how I had summaries, right? You want to have no downtime. You want to do rolling releases. You don't want patching your operating systems to be your monthly, one-time 3 hours off. Okay, you want to be able to scale the throughput of your application. So, and that justifies the reason that you're going to learn how to data model differently. Okay, that you're going to actually have to. I would say that you have to think a lot more as an application developer when you're dealing in eventually consistent world. And you can be consistent, but you're kind of defeating a lot of the purpose if you're doing all your queries at a very high consistency, you're getting a very high latency. And yeah, modern drivers make it so that once you've decided what to do, it's easy to implement. It didn't used to be the case. Done. Any questions? Yeah.
Yeah. So if you have the same piece of data and you want to query it in 2 different ways, you'd have to have different partitioning.
Yeah, you normally have 2 tables, one for each form of the query.
Do you have to manage that yourself explicitly, or can you get the database to manage it? Will it manage it for you?
No, there's no kind of like constraints. There's no way in a distributed database or something at the scale of Cassandra that we're ever going to do like a join or a foreign key constraint, that kind of thing.
Yes, but would it create, if you inserted the single piece of data, would it then create?
No, you'd have to explicitly write it yourself twice.
Okay.
So
if you want to query people by customer ID and then suddenly you want to query them by hair color or something, you'd have to then create hair color data tables.
Correct, yeah, and you would have to backfill that table if you wanted to query it retrospectively.
Yeah.
Which is, again, why I always encourage people to make sure they're using a distributed database because they need the requirements, because it does remove functionality from you. Okay?
Yeah, equally, your customer's hair colour doesn't change everywhere when you change it, which is the other point. Your customer's hair colour doesn't change if you've got it in 2 tables.
Correct.
Was that asking as well?
You find that you'll end up data modeling a lot more log structured. So what's happened, and then you query and work out what's the final state is, rather than having that bank balance. You would store the transactions and then work out the balance from the transactions. You wouldn't keep updating it.
Yeah, so
that makes sense.
Event sourcing.
Yeah. So a lot of people do event systems with Cassandra, and yeah.
Is eBay one of them?
eBay, they're at the Cassandra conference in London, so I'm guessing so, but I don't know about the use case.
I think they likes.
Yeah.
eBay likes Cassandra.
It's amazing. There are many of the big tech companies. So the sponsors of the Cassandra conference in London were like, was it Google, Netflix, Microsoft, and Apple? Like, who's not there? Yeah. But
how do you do backup of your Cassandra cluster?
it's a good question. So a lot of people, some people just think, oh, it's replicated. I'm not going to back it up. I would never advise that because it doesn't stop someone from deleting the data. Cassandra then actually just replicates and deletes it. So the good thing, what we didn't talk about, it would be if I was doing like a more advanced Cassandra talk, is how Cassandra stores it actually physically on disk, the actual files it creates, how it keeps them up to date. Because it does is like you do a write, and forget about the commit log and replaying them during node failures. It just goes in memory. It's on that commit log, don't worry. And then when the memory fills up, it flushes it to disk in what's called a SS table, and they're immutable. And then it empties the memory. And then if there's another disk like memory filling up, it flushes it again. So you end up with 2 SS tables for the same table, right? And then in the background, it compacts them. And they're immutable, so it can do that. We're never updating a file in place, so it can basically build the new bigger file, the combined file, removing any kind of duplicates or anything, and then delete those 2 files. So the reason I explained that was it makes backup super easy. Is because when you do a backup, you run what's called a snapshot. And what it does is it flushes the mem table, flushes the mem table, so you know everything's on disk, and then you can create either what people normally do then is it creates a hard link to it if you're on a Linux system, and then you can put them in S3. So basically, it's already on disk in a backupable way. You don't need to go through almost like the database to get the backup, because it's already, you can tell it to just make sure everything's on disk, and then take those files away. And then if you want to restore it, you can, if it's the exact same cluster, you can just put them back, or there's a tool for basically stringing them back in. Because obviously, if the cluster that you're putting them into is different, those partitions will be somewhere different. So you need the thing putting it in needs to be partitioned over. But if it's the exact same database, you can just drop the files back in. Backup is like a dream compared to any other database. Any more questions?
Is Elasticsearch totally, can it be used with Elasticsearch?
Completely different kind of thing. So one of the main competitors, so Elasticsearch is used lots in case we haven't used it for like storing logs or any kind of textual data which you need to do kind of like searching on. So Cassandra obviously is very limited in how you can query because you have to design the partition key and the clustering keys to be exactly how you want to query it. So there's kind of like an alternative to Elasticsearch is Solar, if anyone's used that. And lots of people actually combine Cassandra and Solar, so that you can basically put text in Cassandra, but it'd be nothing to do with the partition key or the clustering key, but you can still search the text. But that requires the extra component that is Solar.
Okay.
Which is
conjunction with an Elasticsearch.
So it's not remember, Solar is different to like Elasticsearch, so it's like either or.
Okay.
But the one which integrates well with Cassandra is Solar. And if you buy the DataStax version of Cassandra, it comes with Solar built in, so it'll automatically build those indexes for you so you can text search. But bear in mind, building an index for a text document is magnitude slower than writing in Cassandra because you're taking like large text, parsing it, making it queryable. So like if you're going to you wouldn't like run your Solar with your text search, say you're searching like customer documents. You'd have a separate segregated nodes to do the search on, just because that would considerably slow down your operational writes and reads. Yeah.
Apologies if you've already covered this, but how much similarity in principle is there between Cassandra and other databases like Raven or Mongo?
So Cassandra fits into the databases that have been built off the Dynamo paper. So the ones it's most similar to is like RIAC. They're very similar. They're a more key value store. They have got a more richer type system now, but the replication etc. is very similar. They also have vector clocks, whereas Cassandra doesn't. The other one is like Voldemort, and I think Manhattan as well, which came out of Twitter. So Mongo is very different. Mongo is basic document store, so you store like JSON, and it's more traditional architecture. It's a master slave followed by sharding. So you have your node, which is the master you do all the writes to. You have a replica set for the read. So it has single points of failure. It has rebalancing. A Mongo cluster is much harder than a Cassandra cluster. Cassandra cluster use add new nodes, but they're different kind of use cases. Yeah. Any more questions? It's nothing like a graph database. But people do store graph stuff in Cassandra and then make it queryable. There's a thing, Titan, which sits on top of it, turns into a graph database. Any more? So if you want to get going, you want to get playing with it, the best resource is Planet Cassandra. There is the Apache website, but there's nothing much on there. It's just basically where they come at the top, and there's a very under-maintained wiki. There's a separate community site called Planet Cassandra, which has like getting starting guides in every single one of those languages that I just put up. Download guides, a VM if you can't be bothered installing it on your computer, that kind of thing. So that's the best place to go to. Yeah. Any more questions? Anyone want to have a play? Cool. Thanks very much.